Hello, at the beginning let me briefly recall those facts that we already know from the last discussion and provide you with some new details. As we have already seen in previous materials, de Broglie waves for free particles satisfy the Schrödinger equation. However, in a strange way, the classical particle overruns its own de Broglie wave since its classical speed is twice as high as the speed of the wave. Let's illustrate this paradox with a simple example. In old-style television devices, electrons are emitted and accelerated by an electron gun installed inside the cathode ray tube. Then they are deflected by a special magnetic coil in the desired direction. After that, they fly at a constant speed in vacuum, and at the end of the path, they hit a fluorescent screen, creating an image. Television was invented 100 years ago. Theoretical calculations of electron velocities and their trajectories in cathode ray tubes of TV sets were made based on the classical concepts of an electron as a particle with a known mass and charge, accelerated in an electric field created inside the electron gun and then deflected by electrostatic plates or magnetic coils. Thus, we know for sure that electrons fly as classical particles through the vacuum inside the cathode ray tube of a TV set with a certain speed v. If we now move on to the quantum description, then there will no longer be any electrons as particles, nor their velocities or trajectories. Instead, we will have continuous de Broglie waves moving at the speed of 1/2 of the speed v. But then one moves with speed v and hits the screen in the quantum formulation of the problem. We definitely observe this movement in cathode ray tubes of TV sets and laboratory electron guns. These are electrons treated as particles in classical case. Then what are these objects flying with speed v in quantum case? In summary, this difference in velocities of free particles and corresponding de Broglie waves is a fundamental issue. Today we know how amazingly this problem was settled in quantum theory, but we will talk about that much later. Let's not get ahead of the historical course of events and the logic of our presentations. The main founders of new theory based on the wave approach were de Broglie and Schrödinger. Both of them were confident that these questions could be easily resolved in the future through the use of wave packets composed of a large number of de Broglie waves with very close but still different wave numbers. Indeed, we have already seen in the previous story that the speed of even the simplest packet, composed of just two de Broglie waves, is equal to the classical speed of the particle plus a small correction term. If you discard the correction terms in the formulas for speeds and frequencies, then all packets consisting not only of two but also of any other number of de Broglie waves will also move with the classical speed of the corresponding particle. There is, however, one more subtle point here. The speed of each elementary de Broglie wave that make up the packet still remains half the speed of the particle, that is, half the speed of the packet. Thus, if de Broglie waves arise in a bounded region in space, then at the very first moments of time, the packet will overtake its own carrying de Broglie waves and then disappear. In order to fix this problem, we must assume, as I have said in previous stories, that de Broglie waves must arise instantly in an infinite region of space before the packet begins to move. Now we need to check how significant is the role of the discarded terms. In order to do this, we will usually compare the evolution of a packet of 21 cosines with discarded corrections with the movement of a fully fledged packet. We see that the desired packet with discarded corrections a of xt maintains a constant shape, while the actual quantum packet psi of xt blurs in space over time. This is a crucial negative phenomenon. The father of the uncertainty principles, Werner Heisenberg, was the first scientist who pointed out to such an inevitable blur or spreading of quantum packets satisfying to the Schrödinger equation for free particles. Moreover, Heisenberg treated this effect as a proof that the entire Schrödinger's theory was wrong. Heisenberg expressed his criticism of Schrödinger's theory in the same article published in 1927, in which he presented his famous uncertainty relations. Now we will make a small journey into the history. The science now known as non-relativistic quantum mechanics originally arisen 100 years ago in the form of two independent theories. Today everyone is talking about Schrödinger's ket and the Schrödinger equation, also about the wave function and other components of Schrödinger's theory. But historically first was the theory of Heisenberg, Born and Jordan. Initially, it was inspired by original ideas of Werner Heisenberg, published in 1925. The authors called the newly created theory as quantum mechanical theory or quantum theory, and also as quantum mechanics. At that time, many scientists, including Schrödinger, very often referred to this theory as Heisenberg's quantum mechanics. We will also use such reduced names like Heisenberg's theory from time to time for brevity. Historically second was the Schrödinger's theory, which appeared 1 year later in 1926 after Erwin Schrödinger presented his famous equation. The foundations of this theory were laid by Louis de Broglie in 1924, but nevertheless, the complete theory arose only after the publication of Schrödinger's work. In contrast to quantum mechanics of Heisenberg, Born and Jordan, Schrödinger called his new theory wave mechanics. These two theories were totally different from each other. The main goal of wave mechanics in every practical problem was and still is to determine the solution to the Schrödinger equation for the wave function of a particle in a known external field. For example, for a free particle there is no external field, and the solution to the equation is a combination of elementary de Broglie waves already introduced earlier in our stories. Moreover, in many cases we don't even need to solve the equation and use de Broglie waves or other estimations for the wave function. Instead, Heisenberg's quantum mechanics did not work at all with any sort of differential equations of coordinates or wave functions. The main working tools were operations with matrices representing observable physical variables and based on special commutation relations. A little later, the Heisenberg's uncertainty principle was also incorporated into the theory. Due to the use of matrices, physicists very soon began to call Heisenberg's theory matrix mechanics. Since the beginning, the area of applicability of wave theory was significantly wider than for matrix mechanics. For example, already in the first work, Schrödinger quantized the energy levels of the electron in the hydrogen atom, and in the second work, he quantized the so-called linear oscillator, representing movements of atoms in molecules and crystals. Heisenberg, Born and Jordan successfully quantized only the oscillator. It should be noted that the first attempt to quantize the hydrogen atom using matrix mechanics was made by Wolfgang Pauli already in 1926. However, applied methodology was not universal and not very convincing and was based on disputable assertions. In fact, the first consistent techniques for quantizing the hydrogen atom using the principles of matrix mechanics appeared only in the 1960s with the development of the so-called factorization method originally proposed by Schrödinger in 1940. As we saw earlier, within the frames of wave mechanics, it is easier to quantize the energy levels of a particle in a well with infinitely high walls, even without solving the Schrödinger equation. And you know what? Quantizing the particle in the well is not a trivial problem in matrix mechanics. Its complexity is quite comparable to the quantization of the hydrogen atom. However, as Schrödinger noted already in his second publication, his theory and Heisenberg's theory gave the same results when considering the same problems. It became clear that despite the strong difference in approaches, the two theories can still be merged somehow. The best results towards creating a unified theory were achieved by Paul Dirac. Over the course of 18 years, from 1930 to 1947, he published 3 editions of his book The Principles of Quantum Mechanics. The last edition was the most successful. Dirac built his picture of the quantum world on 3 basic concepts: states of quantum systems, vectors of states called him as Brian, ket-vectors, and operators producing and changing the states. Commutation relations from matrix mechanics were also used as the main working tool applied to operators. The Schrödinger equation and the Heisenberg matrices remained unchanged, but the differential Schrödinger equation turned into the Schrödinger operator equation in new terminology. The wave function began to be treated as one of the possible forms of the state vector. Elements of the Heisenberg matrices become the matrix elements of operators acting on vectors of states. In new interpretation, two theories began to be connected with each other in an obvious way. Of course, Dirac summarized in his book numerous results achieved through the collective efforts of many scientists, not just the founders of wave and matrix mechanics. Dirac's book was written in abstract and heavy mathematical language, therefore it's poorly suited for beginners. Moreover, Dirac's ideas did not make quantum calculations easier. However, these ideas determined the global structure and all further rules for the construction of quantum science. Today, we cannot evaluate how good this approach is. This will become clear only in the far future. The name quantum mechanics became the commonly accepted name for the merged theory around 1970. As of today, quantum mechanics is associated mainly with the Schrödinger equation, but then where did matrix mechanics disappear? As a matter of fact, this theory has not gone away. Elements of Heisenberg's matrix mechanics are widely used in modern quantum theory in the form of uncertainty relations, quantum operators, and their commutation rules, and also in specific mathematical techniques related to operations with so-called orbital angular momenta and spins. At the same time, the term matrix mechanics itself has gradually disappeared from textbooks on quantum mechanics over the past 50 years. Formulas and ideas of matrix mechanics are used without their connection to the term matrix mechanics itself. It should be noted, though, that the fundamental constants of so-called operators of creation and annihilation of photons in quantum field theory and operators of creation and annihilation of photons in the solid-state physics both came from matrix mechanics of Heisenberg, Born, and Jordan. It is also important to know that the basic concepts of quantum mechanics can be explained entirely on the basis of wave mechanics with the use of minimal information from matrix mechanics, such as uncertainty relations. I would like to draw attention to one more aspect. As I have noted, Paul Dirac was not alone in his efforts. A new science was born thanks to the efforts of many scientists. During the same period of time, John von Neumann published several successful works devoted to the mathematical foundation of quantum theory. In our time, his book, The Mathematical Foundations of Quantum Mechanics, published first time in 1932 and then reissued in 1955, has become the most famous among his other books related to the mathematical reasoning of quantum science. In general, these works of Dirac and von Neumann had a large number of common points of intersection. However, Dirac's ideas were more suitable for physicists, since he offered a fairly convenient terminology and methodology for discussing and developing physical problems at a high level. On the other hand, von Neumann's ideas were more suitable for mathematicians, since the justification of quantum mechanics in von Neumann's works was done with a focus on the convenient mathematical formalism of linear operators and Hilbert vector space. Scientific approaches developed by von Neumann formed the basis of a special branch of academic mathematics called functional analysis, together with fundamental works of Georg Cantor, David Hilbert, Stefan Banach, and many other mathematicians. Nowadays, there are a large number of statements in internet charts and other publications that quantum mechanics is totally based on the concept of Hermitian operators in Hilbert space. Such an extreme deification of all these working tools is mainly inspired by the formalism developed by von Neumann. Actually, saying this is just about the same as to say that mathematics is the basis of physics. The brevity and categorical nature of such formulations gives an incorrect vision of the real relationship between scientific disciplines and concepts. To achieve the correct understanding, more thorough and detailed explanations are required. Hermitian operators and Hilbert spaces are special cases of linear operators and vector spaces. There are a large number of simple and complex concepts, relations, and theorems, including extended theory of linear operators and vector spaces, that are studied in functional analysis. But quantum mechanics uses very limited set of facts from this branch of mathematics. At the same time, elements of functional analysis are widely used in grounding of Fourier transforms and a large variety of other problems in mathematical physics and computational mathematics. In general, functional analysis is usually included in university programs in fundamental and applied mathematics, but is not studied in university courses in theoretical physics. Therefore, not every theoretical physicist, even being a high-level professional in quantum mechanics, knows the formulations of at least 10% of theorems devoted to Hermitian operators in Hilbert space. There is simply no need for that. Let me illustrate all the aforesaid with a simple instructive example. We hear the clinking of glasses due to elastic vibrations of the walls of the glasses and the air inside and outside. The solutions to these equations of vibrations are very different from the solutions to the Schrödinger equation for an electron in a hydrogen atom. However, the mathematical justification for these very difficult solutions to very different problems is done within the umbrella of the same set of theorems of functional analysis devoted to Hermitian operators in the Hilbert space. In subsequent stories, I will tell you in simple words what Hermitian operators and Hilbert spaces are, why they are amazingly beautiful, and why they arise naturally in quantum mechanics. Now let's go back to Heisenberg's criticism of Schrödinger's wave theory. Today we know that Heisenberg was in error when he said that the whole wave theory is dubious. However, he was absolutely right when he said that the wave packets inevitably spread out and cannot be used to build a consistent theory. Both de Broglie and Schrödinger were wrong in their hopes regarding the use of wave packets. In order to understand the essence of this problem and how significant it is for real atomic particles, we need to look at packet spreading mechanisms. We will do this in upcoming stories. Please do not hesitate to leave your comments under this video if you found this story helpful or if you noticed any mistakes. Your comments are very important to improve the quality of these materials. Thank you for attention.